recordings. Okay, so last time we started to look, just to give you a bit of a background, we were started to look at what is that called? Okay, good. So we started to look at vertex cover with parameters which are smaller than the solution size itself. Okay, so that was our goal, and towards that, we started with a modulator to degree 2 graph, and we said, okay, there are two versions we could ask for the question. In one version, we could ask when the modulator is given, and and that is like, and for that, like, we made an algorithm with running time, if you recall correctly, is like 2 power something, right? 2 power the modulator size, we made an algorithm. Okay, so this one. Okay, and then we asked that, can you come up with an algorithm which is better than 2 power L with that modulator? And the second question we asked, when modulator is not given to us, this was an oblivious version of the question, right? And we realized that what we could do for this is that we had this analogy of trying to solve a problem on input instance without knowing from which graph family or this belongs to. Okay, so hello, can all of you listen to me? Are you able to hear me?
Yes, yes, we can. Yes.
Madhumita, are you able to hear me now? Hello? Madhumita is not able to. Maybe she's okay. So, can anyone talk to Madhumita? If she is able to hear you all?
Hi, Madhumita. Can you hear me?
I think she need to select speaker as well as microphone appropriately. Madhumita is not in this meeting. She thinks she. Okay, maybe she will come. So 2 people ran away. Okay. Anyway. Okay. Hi, Madhumita. Are you able to hear now?
Yes, I'm able to hear now.
Okay, thanks. Okay, so then we said that when we are trying to solve the problem, when modulator is not given, then there are several ways of doing this. One thing is that in polynomial time, we could come up with a approximate modulator and utilize that modulator, use that given modulator to design an algorithm which was non-oblivious, right? Because now we have modulator given to us. Okay, so basically, whenever we are trying to solve vertex cover parameterized by modulator, there are 2 hidden questions, right? One, how to get that modulator and use that to our algorithm, or so that, and there are 2 ways of getting it. One, there could be an FPT algorithm to get there. There could be an FPT approximation to get that. There could be a polynomial time to get that modulator. And once that modulator is given, we can utilize the structure provided by the modulator to design an algorithm for the vertex cover. Okay. So based on that, so we saw a lot of algorithm for degree 1, degree 2, and all kind of things. And okay. So then we noticed an algorithm, that same algorithm that Sanjay mentioned last time, will also work when the modulator is things like S is a feedback vertex set, S is an odd cycle transversal, right? So, but what was not clear to all of us, that how to get an algorithm parameterized by modulator to bipartite graph, or like things of this nature was not clear. And this is why we decided, so what we saw last time is that if I wanted to solve the following set of questions, say I wanted to solve, I will, sorry, it looks like Shrihan has done something funky here. Okay, so today is 8th of April. Okay. So suppose, so I wanted to solve vertex cover parameterized by odd cycle transversal. So what was our algorithm for this? Our algorithm was that, okay, fine. Suppose you have a given the modulator L, okay? You guess which subset goes into the solution, okay? And from the remaining here your bipartite graph, you choose its neighbor here, and you choose this, delete it from your graph, and what is left after that is a bipartite graph where you can compute the vertex cover in polynomial time. And hence this algorithm was running in time 2 to the power L times n to the power big of 1. And the point is, we can notice vertex cover parameterized by any star modulator, any modulator can be solved in 2 power L time if, can be solved in 2 power L time, 2 power L time, if vertex cover is p times solvable on graph class that we obtain after deleting the modulator. Okay. I think, how many of you know split graphs? If you know a split graph, please put +1. Of course, Satya knows split graph. Okay, so what is a split graph? Okay, so a graph G is split if vertex set of G can be partitioned into, if vertex set of G can be partitioned into V1 and V2 such that graph induced on V1 is a clique and graph induced on V2 is an independent set. Okay. Okay. Now, suppose, so what is a set F is split vertex deletion set, is a split vertex deletion set if G minus S is a split graph. Okay. Now imagine that you are given a modulator S for split graph, meaning after I delete this, what is left with me is clique an independent set, and this is my modulator. Now, what is the parameterized complexity of vertex covered parameterized by split vertex deletion set? Anybody?
PT.
Yes. So what's an algorithm?
So we guess the vertices in S that will belong to the solution. And for those vertices in S which do not belong to the solution, you choose its neighbors in C and I. And once we have this click, so basically all of them either cardinality of C prime goes to the solution or cardinality of C prime minus 1 goes to the solution. So this you can check. So you just check if there exists a vertex in C prime which is not adjacent to any vertex in I. So in that case, all of your C prime goes to the solution. Else, except that everything goes into the solution.
So basically, in 2 power L time, we reduce our problem to 2 power L. So we reduce our problem to basically what we do, we reduce our problem to 2 power L instances of vertex cover on split graphs, right? As we have been doing before. So if we can solve the problem vertex cover on split graph in poly time, then we will be done, okay? And how can we solve vertex cover in poly time on the split graph is because, look, what is this? As Sriram was saying, that look, basically you have a click and independent set. So maybe, definitely you need all but one vertex from the click for sure. So you guess which of them it is, except one vertex maybe. And so in fact, like if this vertex also has edged here, you better take him or not. So basically all it tells you that you can solve the problem on split graph in poly time. Okay. So all I want to tell you that so basically whenever you are parameterizing vertex cover by some other object which is smaller than him or anything, you are basically reducing that problem to that many instances of that problem. So that is the overall idea which I wanted to give you. Okay. So having done that, as I promised to you that today I want to do, but while many of these problems are easy to design parameterize algorithm, for one problem, right, we know okay. So what is an odd cycle transversal? Is input is G, K, and question is, does that exist a set, let's say O, subset of VG such that G minus O is bipartite, right? I haven't showed you any algorithm for this, and that was my agenda item last time, that I wanted to design an algorithm for this problem. Have I given this homework to anybody? This question? Sanjay, what was your homework problem?
Degree bounded deletion.
Okay, great. Prateek, if he's around, seems to be there. Okay, excellent. And did someone get odd cycle transversal? No. Someone had feedback vertex set, if I recall correctly.
Yes, sir, I hope.
And someone had feedback vertex set in tournament.
No, I have connected vertex.
Oh, you have connected. Okay, fine. It doesn't matter. So nobody got odd cycle transversal. It was intentional. Okay. So I have taught you several set of tools and techniques. Several. Okay. Branching, kernelization, this and that. Do you see any of them being applied here? Of course, many of you have seen an algorithm in earlier, but like if you would have not known algorithm and with the methods and techniques that I have resolved you, can you even try to think of how to go about even attacking this problem? Okay. So how did we start initiating the problem for vertex cover, designing an algorithm for vertex cover? We said, okay, we actually started with n equal to vertex set of G, right? Can you give me any algorithm to find odd cycle transversal, which is FPT in N? Where N is number of vertex set in my graph. Forget about K as a solution size. If N is my number of vertices, could you design an algorithm which is fixed parameter tractable in number of vertices?
Try all subsets.
Yes. Why all subsets? Does it make sense to everybody? Like, do you all agree to this algorithm? Yes, excellent. Okay. Okay, so all of you seem to agree in this algorithm. And then we were trying to do a lot of hard work to design an algorithm with running time 2 minus epsilon to the power n. Okay. So n is much bigger parameter than k. So let's see if we can, with a parameter which is larger than, which is potentially much larger than k, can we design something which is non-trivial? Because whatever is like, can we do something which is better than brute force? Okay, because any parameterized algorithm by nature of its by its nature is a smart way of looking into the solution space. So solution space consists of all n choose k subsets, and FPT is a smart way of looking into that solution set. So now I want to do better than n choose k. Can we do much, like not much better, but I ask, can I at least do 1.99 to the power n kind of algorithm? Okay. Can I exploit the fact that n is potentially larger? Okay. So what should we do? Okay. Let's, as always in parameterized algorithm, we draw 3 circles, one for the modulator, and we draw another thing below it, which is the graph class we are going to belong to. Okay. So now what graph class we are going to belong to? We are going to bipartite graph. So we will draw 2 circles. So this is parameterized complexity. What is this? For OCT, the parameterized complexity consists of 3 circles, 1 horizontal and 2 vertical, and then some edges drawn like this. So according to Sushmita, this is all that I do, is to draw some pictures and write some K somewhere. So yeah, so let's do this. Okay, but what does this teach you? What does this tells you? What are these objects, left and right? What is left? What is this? This is? This is? Let's say this is A and this is B. What is A? A is independent set and B is independent set. I actually wrote an algorithm now. Okay, so let me ask a question. Okay, imagine I gave you A. I gave you A for free. Okay. Now can you get me O? I gave you A for free. Out of these three sets, I gave you A for free. So Ankit is saying something. How many of you agree to him? Do you understand my question? So if I gave you A, okay, then what is O? Given A, what is O and B relationship? Okay. Imagine for now that I wanted to, okay, you get my question? Right? Yes. So basically, if I gave you A, O is nothing but finding so basically, O is a vertex cover of, okay, then let's say, I will say the following. G minus A has OCT of size at most K if and only if G minus A has vertex cover of size at most K.
No, it should be G, na, not G minus A in the first line.
No, I mean G minus A because I gave you A.
Okay.
If I did not give you A, then you can't do this. Is that fine?
No. So, I mean, if G minus A has an OCT of size at most K, that means we are finding another set that splits the remaining graph into a bipartite graph. But can't we just say that G has a OCT of size at most K?
What?
I don't understand the relation, but like, why would G minus A have a vertex cover of size at most K?
Okay. Okay, you're right. Maybe you're right. This is what I should say. Is this fine? Okay. Or I'm just trying to get to an algorithm. Okay. So now, so all of you understand what A is. Okay. And okay. So good. Okay. So this is one nice thing. Okay. So I have O, I have A, and I have B here. So what I'm telling you that suppose somehow I know my A, then in the remaining graph, I have very efficient algorithms to help myself. Okay. Now let's see ourselves. How can we find A? So A is what? All of you people said. A is what?
Independence.
So how many independent sets a graph can have? How many independent set a graph has? Can have independent set.
At most 3 to the power of 8.
Oh, really, Sona? How many independent set this graph has? Hmm?
2 to the power n.
Yes, it's 2 power n. You take any subset that is an independent set. So what is, so Sonak, what did you say? What number did you say?
3 to the power n by 3.
What was 3 to the power n by 3?
Number of maximal independent sets.
Yes. Number of maximal independent sets. Okay. Excellent. Right? So I need to know A. If I can only show that A is an independent set, then I can only say, let's enumerate all A, then it's like 2 power n. Right? But if I can also show that, no, I can actually take A to be a maximal independent set, then probably we can do some saving. Right? So now I will ask myself, in our picture, here is our picture, O, A, B. Can we assume A is maximal?
Yes.
Okay. Why? Because if A is not maximal, meaning what? I can add some vertex from here, or I can add some vertex from here and make it maximal, right? What is the meaning of maximal? A set A of independent set is not maximal because there is some vertex outside which can be added to A, right? So if I do that, what will happen? Only thing could happen potentially is that A becomes, it can be like this, but the size of O can only decrease, it will not become more. So I can assume that if I'm looking for an odd cycle transversal of size at most K, then there is actually one where one side is a maximal independent set. Am I right? Okay. Is that fine or not?
Yes.
Right? Is this clear to everybody that I can assume in my configuration that A is a maximal independent set? Okay. So what did we prove? We actually proved there exists an odd cycle transversal of size at most K, OCTO of size at most K, such that in bipartite graph G minus O, we can take one part to be maximal independent set in G. Okay. Is it fine? This is what we showed. So what is now our algorithm? Enumerate MIS A of G, and secondly, compute minimum vertex cover which is equal to maximum independent set in G minus A. Okay, that's it. Is this fine? If for any A we get O of size at most K returned. Is that fine? Minimum vertex cover O right? This is my whole algorithm. Okay, what is the running time of this algorithm? So what was the best running time of maximum independent set we get? What was the best maximum independent set or minimum vertex cover algorithm we got? Parameterized by n, number of vertices. What was that? What did we make?
1.45.
Is that what we made? Do you realize an algorithm that can do minimum vertex cover also can compute maximum independent set? Yes or no?
Yes, yes.
Right? So what is the best?
1.32.
That was with respect to K, solution size. And I asked, what will happen if you replace?
There's some 1.27 or 28 something.
Exactly. So actually we made these kind of algorithm for minimum vertex cover. Now you please tell me, what is the running time of this algorithm? Here is it. Enumerate MIS A of G. How many of them are there? How many can be enumerated? Maximal independent sets. Just now someone was telling me the numbers.
3 power n by 3.
Okay. And now for each of them, how much time can I take to solve minimum vertex cover in the worst case?
1.28.
So what is this? Can someone tell me? Is it less than 2? I don't know.
It's 1.8 something.
1.846, right? Something like this. Is that fine? So it seems that we are doing some savings. So if we wanted to do somehow we found some other clever way to get this A in f of k time, then to find OCT, we could apply our old k vertex cover algorithm, right? And you realize if we wanted to solve k size vertex cover and someone gave k size OCT, given someone gave me that A, then in the given graph, all I needed to check does that is a vertex cover of size at most k, for which we have made so many algorithms, right? But when I wanted to try n, it was easy for us because look at this, like, oh, we think for a minute, we say, okay, we need to, what is this A? Oh, this A is a maximum independence, but that could be too many. So can I replace? So whenever I'm getting a maximum independence set, I always try to see if I can get it maximal independence set. Okay. Okay, because then the enumeration reduces drastically and then I'm doing something. But notice, why do you think that this running time of this algorithm should be way much better than this running time? Why do you think? Do you think it should be much, much better than this? And why do you think that? Okay. Or rather, let me say, please give me a better analysis of it. At least do better than this as an analysis.
Sakit, I have a question or maybe suggestion. So it's 1.28 to the power n, but we need not to find the vertex cover in the whole vertex set now.
Yeah. So where? Look, yeah, you're right. We are finding the minimum vertex cover in G minus A. I have written my algorithm correctly. Look, I am doing in G minus A, whatever I was promised. But G minus A could be as big as N. So unless you tell me something nice and interesting, all I can tell you is this. You understand my point? Like, first of all, do you understand this analysis of this algorithm at least? Like, do all of you understand this analysis of this algorithm? Hi, Pratik, do you understand?
Yes.
Yes? Yes, no?
Yes.
Okay. Kushal?
Sir, yeah, but bit confusion. I have to see it once again.
This is the algorithm I wrote. Okay. I multiplied, first is how many numbers of them are there, which is 3 to the power n by 3. And what is the worst case time complexity for the second? And I just multiplied both of those numbers. In one slide. This is my algorithm. I enumerate all maximal independent set A of my graph, and I delete that A. And in the remaining graph, I either find a minimum vertex cover O or a maximum independent set and say, look at this guy. This is your independent. This guy is going to act as your odd cycle transversal. Now, why it is? Because look, I already have an independent set. So what is a bipartite graph? It's basically union of two independent sets. So what is the minimum number of vertices should I delete so the graph is too colorable? Or graph can be partitioned into two independent sets, or graph can be covered by two independent sets. They all are same object. If graph can be covered by two independent sets, it means you take out the first independent set and the remaining also forms an independent set. So covering and partitioning is same object. All right. So what I'm saying, you enumerate maximal independent set. So I have got one part of my bipartite graph that I want. And in the remaining graph, what is left? Some vertices that need to be removed so that whatever is remaining is an independent set. And that is precisely the question of vertex cover. Now, how many such maximal independent set we have? That is exactly the bound of 3 to the power n over 3. Okay. And what is the second step? After I have deleted this maximal independent set, in the remaining graph, what is the algorithm's running time to compute minimum vertex cover or maximum independent set? And that is this time. Right? And I just multiplied them to get this to number. But as Nidhi observed, that look, you should, my point is this algorithm does much better. And I wanted you to know, can you come up with one way to reduce the running time of this algorithm? And one observation Nidhi has that, look, actually you are computing minimum vertex cover on not whole graph, but on a graph which is G minus A.
Is the point that the second step computing the minimum vertex cover, so the algorithm, it computes even when the minimum vertex cover is greater than k. So we have to stop at some point where if
No,
we can't go.
look, K is like, K could be anything. I could have just asked you minimum or odd cycle transversal question. It doesn't matter. I will give you K, which will give you a worst running time. Okay. Okay. What is, let's say, n choose n over 5? Is it,
Had
huh?
we had an n choose alpha in approximation, like
Formula? Yeah,
yeah,
so what is that? I'm just saying use that.
yeah. So the formula was 1 by alpha equal to 1 by alpha to the power alpha.
So what is 1 by alpha here? It will be
5.
5 to the power?
The power 1 by 5.
Correct.
Times 5 by 4, because it is 1 by 1 minus alpha to the power 4 by 5.
Okay, so
The whole power.
and according to Satya, this number is 1.649. Okay, is that fine? Correct. Doesn't matter. 1.6. So I'm just giving you some example. So what I will say, okay, let this sum this. I'm going to sum this. I'm sum this maximal independent set of size at most n over 5. Okay, plus maximal independent set of size at least n over 5. Okay. So now in the left hand side, I'm going to say, hey, how many maximal independent set of size at most n by 5 is? Okay, I don't care. They're at most n choose n by 5 times, and then running time is 1.28 to the power n. But for the other, I don't know how many maximal independent set of size at least n over 5 is, but at most 3 to the power n by 3. But what is the size of G minus A now? At least, at most,
N minus
correct?
n by 5.
Yeah, 4n by 5. So what is the running time of this algorithm? I'm sure it is better than the last time. No, 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 no. It should be worse, no? It is worse because n choose n by 5 is much more than 3 to the power n over 3. Okay? So you have to go even lower. How much is n choose n by 10? Is it less than 3 to the power n over 3? That's all that I care. Someone should tell me the number. Oh, it is 1.38, no? Okay, so if I do this, then this is going to be 9 by 10 n. But what is this left hand side? This is going to be this is like 1.80 something, and this is 1.38. This is like 1.7664 to the power n. Okay. So I just wanted to give you just proof of concept. I was not trying to optimize anything. Okay. Okay. Yeah. So basically, which implies that this running time is 1.80 to the power n. And there are actually, people have also studied how many maximal independent sets of size at most k are there, and there are good formulas for that. Okay. If you use that nicely, then you can actually take this algorithm and reduce this running time to 1.67 to the power n. So this much you can get. Okay, so if you use this algorithm, you could do this. Okay, but let's go back and look at this picture again, and let's do something different. Okay, and that is what will lead us to. It will get us back the vertex cover algorithm. Okay, so let me. Okay, so you at least agree to one algorithm for odd cycle transversal that runs in roughly 1.8 to the power n, but we can do much better, as you will see now. So, and that is also one reason why I never tried to optimize this algorithm. Okay, but one should view this as a starting point of our algorithm. Okay, okay. So one naive question was basically what happened is in this algorithm. Okay, so let's like a movies. Let's do take two. Okay, so that was take one, and then let's do take two. So take two, we still have this O, and we have A, and we have B. Okay, now basically, what is A union B? A union B, I can think of this A union B as maximum size, maximum sized vertex subset of VG that can be covered with two independent sets, or that is equal to that can be partitioned into two independent sets, or which is two colorable. Okay, as usual. So basically, what is this? It is a maximum sized object. Okay, it's a maximum sized object that does certain job. Okay, now it is a very tempting thing, no? So notice what happened, right? What happened is that in this graph, look, if I told you what A is, in this graph, basically you were solving maximum independent set problem. Okay? You get my point? So I want to do the same thing, like in some sense, I want to do the same thing in OA. So suppose similarly, if I gave you B, then in this G minus B, it becomes a maximum independent set question. Right? So what would ideally be that, can I come up with a graph with the following property? Can I come up with like somehow I want to have two graphs. Okay, so look, imagine yourself. I make two graphs. Okay, I'm making two graphs. I take two copies of the same graph. Okay, I take two copies of the same graph G. Okay, I want to find an independent set here and an independent set here. Okay, with the following property, they should not intersect. How can I do that? You get my question? What can I add edges here that will force me that I don't pick the same vertex in the both sides? So what is my goal? I want to find, so suppose call this graph G star. Okay, so what is in G star? In G star, I will find a maximum independence. I want to find some independence set with the sum property that if you look at in the first graph G, it is an independent set. In the second graph G, it's also an independent set, but the vertices are different. How can I ensure that?
So we add an edge between two copies of the same vertex.
Okay, oh, that's a good suggestion. How many of you agree to that suggestion? So what is he saying? He is saying, you suppose graph G, call a first copy of graph G1 and second. So suppose this is like V1 to Vn, and I call these vertices Wn to Wn, but they are same graph. And V1, W1 represent the same vertex. So what Ananya is saying that add this edges, because now if you find a maximum independent set, you can't keep both copies V1, W1 because you have physically put an edge between V1 and W1. Okay, you have physically put an edge between Vn and Wn. You have physically put an edge between Vm. So now you find a maximum independent set in this graph, in G star graph. What does that corresponds to? Now I ask you, what does maximum independent set in, or forget about maximum, what does independent set in G correspond to? What does independent set in G star correspond to? Please tell me. Okay, so here's your construction.
Saket,
Yes.
I'm sorry, I did not follow Ananya's argument. Could you please repeat?
Okay. So what I'm saying to you, what is the graph G1 and G2? G1 is same as G. G2 is same as G. Okay. So now look at, suppose graph G is U1, U2, Un. Okay. I call the copy of U1 in G1 as V1 and its copy in G2 as W1. U2 as V2 and W2. But okay, now I say, look, what I wanted to find an independent set of G star graph, which was just disjoint enough to copy, such that I don't pick the same vertex both sides. So what did Ananya said? Okay, if you want to just ensure that, then please put an edge between V1 and W1. Now, the moment you put an edge between V1 and W1, you can't have an independent set in this graph G star that will put both copies of the same vertex because you physically went and put an edge between them. No, that's all.
Thank you.
Okay. So now my question is, what does an independent set in G star correspond to? What do they belong? What do they? And what are they? So suppose I is an independent set in G star. What does it correspond to?
To a bipartite graph in G.
Why?
Because we got two independent sets. That two independent set can be seen as two partites in G.
So this is one independent set. And this is another independent set. Because you have put the same edge between the same vertex, these independent sets are like basically different. And now if you project back, they are here, but they are still independent set of the same graph. Only thing you cannot ensure independence is independence between among these vertices. But okay, it's only that edge is here, no? Okay, so let me. Okay. So how does an independent set in G star looks like? It's an independent. So look at that G star and look at, so I is an independent set in G star. So let I1 be I intersection VG1. And what is an I2 is I intersection VG2. Now look at the vertices of I1 in G. That is an independent set. Okay. Vertices of I2 in G. That is an independent set. Okay. So what did you get in G? Here your G, you got one independent set, you got another independent set. Okay. So if you got some set of vertices which are defined into two color classes, doesn't matter what edges they have between them. But this is a
Bipartite.
This is a bipartite graph, right? So every independent set in G star corresponds to what? A bipartite graph in G, right? So what did we learn from here? So we are able to see every independent set in G star corresponds to a bipartite graph. That's the first thing. And what does every bipartite graph corresponds to? Every bipartite graph in G corresponds to, what does it corresponds to in G star?
An independent set.
Yes, because why? Because look at this bipartite graph. It means it can be partitioned into two independent sets, right? Okay, so you take this guy in G1, you take this side into G2 because no common vertices. Okay, this V1 and V2 or this AB graph G star A union B is an independent set. Right? So what are we able to see? We are able to see that every independent set corresponds to in G star corresponds to a bipartite subgraph, and every bipartite subgraph corresponds to an independent set in G star. So what have we learned from this? Okay, so we can say G has a bipartite subgraph, bipartite induced graph of size L if and only if G star has an independent set of size, right? Is that fine? Is this statement fine with everybody? Okay. So if the statement is fine with all of you, can you design an algorithm for finding an odd cycle transversal in G, or like using this, can you design an algorithm for odd cycle transversal in G?
So if you got the
What?
If
Yes,
you
Sonak,
got
go
the
ahead.
Okay.
Hi, Sonak, go ahead.
Yeah, construct the graph G star and find this maximal independence.
Maximal or maximum independent set?
Yeah, maximum.
Okay. And then that maximum independent set corresponds to maximum bipartite subgraph in G,
G.
which means its complement corresponds to
What's complement?
complement of this maximum bipartite subgraph corresponds to
OCT.
Minimum OCT.
okay. So there is some very beautiful property of this. Okay. So here's my algorithm. Okay. What is my algorithm? Given G, compute G star. Okay. What is this? Given G, compute G star. Compute, because compute minimum vertex cover of G star. Let X be this. Then VG star minus X equal to I is maximum independent set of G star. Third, project I on G and let O be the complement of I in G. Right? So what is the running time of this algorithm?
One point two.
What?
1.28 to the body.
1.28
The body.
to the power n?
2n.
Because G star, vertex set of G star is 2 times vertex set of G, which is 2n. Right? So now what is the running time of this algorithm is?
$1.64.
Okay. So if you use the best known algorithm for maximum independent set and or minimum vertex cover, you will get something much below, like you will get below 1.5. Okay. So these algorithms we constructed in the class. It's not something which is okay. So now I want to go back to G and G star. So look at G and look at G star. Okay. If you had L sized bipartite graph, where what did it become? L sized independent set. But a K sized OCT will become what?
Vertex covered.
But what is its size?
In
2n
my
minus L.
What?
2n minus L in terms of K.
So K size OCT became what? No, like if I just told you, oh, this is an OCT, what can you say? This is a K size OCT here. What it becomes?
N plus K.
Hmm?
N plus K.
Size. What is the size of the vertex cover that it becomes? If it is a k-sized OCT, what is its complement?
N minus K.
N minus k-sized bipartite
Bipartite
graph,
graph.
which will remain an N minus k-sized OCT, sorry, independent set. So what are we getting? So this is, so what size, a k-sized OCT becomes what? What size vertex cover?
K-sized vertex cover. Right? Because
Really?
K-sized of
N plus
OCT
K.
becomes
N plus
N minus
K.
K-sized independent set.
N plus K.
Wait. Look, my construction preserves the size of bipartite graphs. It does not preserve the size of OCT.
Oh.
It preserve. Look, how can it preserve, right? It can only preserve one object if I just double the graph. So if I have a k-sized OCT,
2K plus L size vertex cover.
don't talk in terms of L.
Oh,
There's nothing called L. If there's a k-sized OCT, it means it has n minus k size bipartite graph. Talk in terms of that.
N plus K-sized vertex cover.
Then it has a vertex cover of size n plus k. That's all that I can say. Look, here it is k, and this is n minus k, and this is going to be the size of independent set. This is n minus k, but the whole thing is 2n. So 2n minus n minus k, which is 2n minus n plus k. Okay. So now if I have to write, so what, so now write, G has an OCT of size at most k, if and only if G has a bipartite induced graph of size at least n minus k. Is that correct? Is this statement fine?
yes.
Okay. If and only if G star has independent set of size at least n minus k. Is this fine?
Yes.
If and only if G star has vertex cover of size at least n plus k. This is all that I wanted to say.
It should be less than
Should be
equal to
at
that
most.
one.
Wait, yes, you are right. Okay. You are absolutely right. This should be at most n minus k. Okay. Is that fine with everybody? This is where I wanted to reach now, for now. Okay. Okay. So I would really like to know if all of you followed up until now. Okay, excellent. Okay, so ultimately, so what does this if and only if tells us? Right? One potential way to solve OCT is what? Find what?
Find the
Solve
vertex.
OCT.
Vertex cover in G system.
Okay, but like suppose no. Okay, one potential way to solve, or one potential way to design f of k n to the power big of 1 time algorithm for OCT is by designing what?
f of n plus k into.
But
That
will
is
that be an
not-
FPT algorithm?
No.
So what do you expect? So what should you, first of all, what you should find, what you have to find? Is to find what? Vertex cover of size at most n plus k on G star in time what? What time can you take?
f of k n to the power of 1.
Yeah, some h of k times n to the power 1. You have to find a vertex cover of size n plus k, but the running time you're allowed to take is only h of k. I mean, whether we can achieve or not achieve is an entirely different thing. But all I want is, do we have clarity of the question we are trying to address? That's all that I'm asking. If we could find a vertex cover, because given a G, we can construct G star in poly time. Nothing. Take 2 copies of J, match edges between them. Is that right? Is this clear to everybody? Hello? Okay, at least 5 of 6 of you seem to follow. Okay, so I want to go back and look at my graph G star. Okay, back. Okay. Here is my graph G star, which is basically copy of G1, a copy G1, which is isomorphic copy to Z, and G2, same copy, same copy, same copy. And what did we do? We added an edge. Okay. I want to make following statement. Any vertex cover in G star at size at least
n, because you have a matching of size n.
because we have matching of size at least n. Is this statement okay with everybody?
Yes.
Okay. Does it reminds us of a problem we wanted to solve? Does this remind of any problem that we wanted to solve? Anybody? Does it rings a bell? Something which we have discussed before, not algorithm, the problem.
OCT?
No. There was one day that I was talking about, just a lecture before this. It's on the YouTube, you can have a look. In what context this problem showed up. You all are in front of your laptop, so just look at, all lectures are there. In what context that question came up. Have we ever discussed that question? Like anybody remembers? Anybody? So I think I wrote the following problem. Vertex cover. Input is G. Question is K. Okay. And what is the running time of this algorithm we wanted to expect? Since F K minus maximum matching of G times n to the power big of 1. Didn't we talk about this question? Have we talked about this question before?
Yes.
Okay. So how many of you remember this question now at least? All of you, do you remember? Or either way. So suppose if we did had an algorithm for this problem, if we had an algorithm for this problem, vertex cover, let's say above matching. Just okay. Suppose I call this problem. Suppose we had an FPT algorithm for this. FPT algorithm for above, okay, vertex cover above matching question. FPT running in time, say h of k times n to the power big of 1. Or h of not. Then suppose we had. Now, do we have an algorithm for OCT? How many of you see an algorithm for OCT now? So facts. So to solve OCT on, so look at this. Okay, so here is G. What is the goal? Solve OCT. G and K. N to the power big O of 1 time G star. You wanted to solve K, but now it becomes N plus K, but solve vertex cover, right? But N is a size of maximum matching. Okay, excellent. So now I will run this algorithm, which runs in time h k minus maximum matching of G star times n to the power big of 1, right? Which is equal to h of k, n plus k. Okay, no. This is okay. So what is our okay? So I think there are far too many k's. No. So this is
H of k prime minus maximum.
no. This is like okay. So this is h of n plus k minus this. This is my algorithm, right? Because what is the running time of this algorithm? Is k minus mm, where k is my vertex cover. So this is my algorithm, which is n plus k, n times n to the power 1, which is h of k times n to the power big of 1. So, which implies we have an algorithm for OCT running in time Is this flowchart clear to everybody? So I wanted to solve OCT on G comma K. In poly time, I reduce it to this graph G star, where I want to solve vertex cover, but vertex cover size is large, n plus k. But we observe that n is the size of the maximum matching. So we are not going to apply any vertex cover algorithm, but a vertex cover algorithm which runs in time, vertex cover size minus maximum matching of my graph n. So, okay, so my vertex cover that I'm looking for has size n plus k, but the maximum matching size is at least n. So n will get cancelled. So this is a function of k itself. But what was k? Was the size of odd cyclic transversal. So although we are computing a vertex cover which is very big of size n plus k, but the running time is governed by the size of OCT, which was k. So basically we have given a reduction, a polynomial time reduction from an odd cycle transversal problem to a problem called vertex cover above matching. Okay, all well? So is this fine with everybody? Okay, so now let's talk about another problem. Okay, so let's go back. Okay, remember we wrote linear programming for vertex cover. What was the linear programming for vertex cover? Minimize summation xv, v and v, xu plus xv is greater than equal to u, 1 for all uv in my graph, which are edge, and xu is greater than equal to 0 for all u in my vertex set of G. Okay, let LPVC of G be the optimum value of this. Okay, optimum value of this. Okay, now is that fine? Optimum value of this linear program, like given a graph G, LPVC be the optimum value of linear programming relaxation. Okay, so what we know that K, which is basically an integral solution of vertex cover, is also greater than equal to LPVC of G, because relaxation allows you are minimizing problem, right? So that will be only smaller than the integer programming relaxation, right? So what we know, K is always greater than equal to LPVC of G. If K is strictly less than LPVC of G, then you can say there is no solution at all, because integral solution can only be larger than the relaxed solution. Okay. So this also provides a lower bound. So now we can have another question. What is that? So we can say vertex covered above LP. Okay, what is the problem? Problem is all over again. It's just like G and K, right? Question is, does G has a vertex cover of size at most K? Okay. But what is my parameter? That is the most important, interesting thing. So the running time you must measure in terms of K minus linear programming for vertex cover relaxation of G. That is my running time. Okay. Okay. Let's see my observation one. How many of you agree to this? Anybody that see a proof for this? Okay, wow. Okay, so yeah, help. Okay, Satyabrata, help. Your voice is very low. Could you be louder?
That's why I always write there.
What?
So that's why I always write there. Zoom has a problem.
Okay. Okay. So anyone else then? Let's see if I find someone else who generally don't write.
Actually, maximum matching problem is just dual of a discover problem. So I remember on that way.
No. Give me a proof. And it should be a proof.
So,
Yes, Ajay.
given a maximum matching, like one edge in the matching connects two distinct vertices, and the constraint of that edge tells us that the sum of the values of those vertices corresponding to those vertices must be greater than or equal to 1.
Right. Okay.
So
what is he saying? Yeah, you're right, Ajay. So what is Ajay is saying that forget about, look at this constraints, no?
बोलते ही कम है जूम में बोलते ही कम है लोगों से पूरा है ना जब चुका करके कम हो जाएगा
Satya, can you mute yourself? Okay. So look at this constraint as copy. Okay. It's like, it's very nice. Okay. So what he's saying is that look at this edge constraint, right? Let's fix a matching value, M, matching E1, E2, say EQ. And E1 is like V1, U1, or U1, V1, U2, V2, UQ, VQ. What is the property? All these are pairwise disjoint. Okay, these are pairwise disjoint. Now there's an edge. So what we have, XU1 plus VX V1, this value is at least greater than or equal to 1. XU2 plus XV2, this value is also greater than or equal to 1. All right, and this is true about any agent. So in particular, the value of these guys are also. But what do you know about this? These are vertex disjoint, right? These are this. So now, what is summation? Summation is over all V in V something, right? So it is also has summation V in V, say V minus vertex set of M plus summation V into vertex set of N, and then you add. What is this? Basically, it is, right? If I look at this part of the summation, this is basically XU1, XV1 plus XU2 plus XV2 dot 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 XUQ time plus XVQ, right? This is equal to greater than equal to 1. This is greater than equal to 1. This is greater than equal to 1, which implies that this part of the sum is greater than equal to Q, which is equal to the maximum matching. So this is some other positive quantity. It can only be larger, which implies that linear programming relaxation of any graph is greater than equal to maximum matching of G. And Somin said something about duality of vertex cover and matching. Is it true?
Yes, sir. Actually, dual of, if I consider vertex cover as primal, then it's dual. I think it will be maximum.
Okay, so here's an exercise for you. You're talking about dual, primal dual with respect to LP primal dual. Am I right, Somin?
Yes, sir.
Okay. Please, can you write a proof that vertex cover LP is a dual of maximum matching LP? Can you write it down formally and tell me? On general graphs.
Yeah, right now?
No. Do it and just give me after a few days.
Okay, sir.
Please try to work it out. Okay. Thanks. Okay. So why did I bring this up? Okay. So now imagine that if we had an FPT algorithm with running time f k minus LPVC of G times n to the power big O of 1, does this imply we also have an algorithm with running time this? Tell me. I have everything here.
Yes.
Yes?
LPVCG is at least maximum matching.
Okay, so if we had this algorithm, okay, so I'm like, as I told you always, like I'm only asking very simple question. G is upper bounded by f of k minus, what is LPVC of G? Is a larger quantity than matching. Okay, so yeah, so if it is a larger quantity, you are subtracting, like k minus that larger quantity is less than if I subtract something smaller. Am I right? So what did we learn? So we learned that what did we learn now? So basically, we already have started to make our complexity question. Okay, what have we started to make? A slightly complexity question. So suppose our complexity is, here is above, what we wrote? Vertex cover above LP, right? Okay. So here is vertex cover above LP, and there was a vertex cover above matching if you have an algorithm for this, an algorithm for this implies an algorithm for this, right? Algorithm for this implies an algorithm for odd cycle transversal. Okay. What about split vertex deletion? That the problem we started with, we also talked about now. So remember the graph class that we were considering. What was that? What was that split vertex deletion problem? Split vertex deletion problem was input was GK, and the question was, does there exist a set S subset of VG? G minus S is a split graph. Okay, and my parameter was K. Do you think if we had an algorithm for vertex cover above LP or vertex cover above matching, we can solve split vertex deletion problem also? This problem? Okay. So that's your exercise for the night. Okay. Think about it. Okay. So tomorrow morning, we are going to spend our time on trying to design an algorithm for this. So that's our goal for tomorrow morning. And the moment we will have an algorithm for that, then we would have got designed algorithm for various other kind of problems, which we have seen today in our class. Okay. So until you have further question, I'm done for today's lecture. And this is a question for you to think how, if you had an algorithm for vertex cover above matching or vertex cover above LP, I think the best is to think vertex cover above matching, then you could solve this problem. There are direct algorithms, but please don't do that. I want you to think in this direction. Okay. Any question? No question? Then good night to all of you. See you tomorrow morning at 9:30. Okay.
Thank you, Sandeep.
Good night.
Good night.